So here we are for 6.7, but I'm going to start with the problem at the top, application of a composite function. Basically, the computer store is offering a $40 rebate along with a $20 discount. Let X be the original price of the item. Write a function that represents the sale price after the 20% discount. So if you get a 20% discount, you pay 80% of the price. And in a decimal, that would be 0.8. So this is what an 80% discount looks like. That's an 80% discount. Okay, so no talk about the rebate yet. When we go right here, you can see this says, okay, let's do the discount on the rebate. Let's do the discount on the rebate price. So this says do the rebate first. So my price is no longer going to be X. My price is going to be X minus 40. $40 rebate. Okay, and then I want to pay 80% of that. So there is that function, okay? Over here, if I'm taking a rebate of $40 off the price, this would be the new price. This is just with a $40 rebate. Here, if it says, okay, take the discount first, then apply the rebate. Okay, so 0.80 X, then apply the rebate. Okay, so, what do we think is going to be better here? If you go ahead and look at this multiplied out, hopefully you can see, this gets a 80% of X, this gets 80% of X, minus 32 bucks, minus 40 bucks. This is obviously going to be the better scenario. But if we kind of compare this formula to before it's obvious, which is the better, let's just kind of think about what happens here. Here, you're taking a low price at 80% of price and minusing 40. The 40 stays the same, okay? So you're getting an 80% off, this bigger price right here. This is the full price. You're getting 80% of that. So a lower price right here minus the 40. Here, you're minusing the 40. You get the minus 40 either way. But now you're only taking 80% of, 60 bucks. Here, you take 80% of 100. And take 40 off that. Here, you are just getting 80% of 60 bucks. So just watch how it plays out if you were to plug in, some numbers. So if you said D of R of X of 100, let's put 100 in. I mean, I know a computer's not 100 bucks, but that's just for the sake of ease of numbers. Let's do 100. So this would be 80%. You're going to do the rebate first of 60. So 48 bucks. Over here, if you did RD of 100, you're going to do the discount first. Okay, so that's 80 bucks. A lower, excuse me, a lower, starting price before the rebate, and you're going to pay 40. So that's the better case. Explaining in complete sentences what each one represents. Basically, DRX means to rebate is applied, then the discount is taken, whereas R of D of X is discount is applied, then the rebate is taken. All right, so there's just a little word problem with composition of functions. Okay, 6.7 is inverses, inverse functions. Explain what the net result is when a function is followed by its inverse. They basically undo one another. So some examples, if I have a square root and I square it, they undo one another and get to X. Okay, and X is neutral for equations. It's this neutral number. If you plug in X, it doesn't change anything. 3 plus a negative 3 is 0. So these are inverses, add, subtract, positive, negative. They get me to 0, which is neutral for addition. It doesn't change value. And then 3 times 1 over 3, those are inverses. 3 and 1 over 3 sort of negate or undo. They get you to 1, and 1 doesn't affect multiplication. 0 doesn't affect addition, and X doesn't affect equations because they just keep it neutral. All right, so let's do some inverse functions. So suppose we convert the number of feet to the number of inches. And so we're going to let the number of feet here be my x. And so to convert 1 foot to inches, you'd multiply by 12. So this function would be 12x. 2 feet would be 24 inches. 3 feet would be 36 inches. Okay. Suppose we use a function that converts the number of inches, let that be x, to feet. So if I have 12 inches, that's 1 foot. 24 inches is 2 feet. 36 inches is 3 feet. So this is going to be this x divided by 12. So are these inverses? Yes. And look what happened to the ordered pairs. The domain of the function 1, 2, 3 became the range of the inverse 1, 2, 3. The domain of the function is the range of the inverse. Okay, and the range of the function 12, 24, 36 became the domain 12, 24, 36. So remember, domain is x and range is y. So they interchange. Okay, so just like x and y interchange, all right, x and y interchange. All right, so domain and range are going to interchange because domain is x and range is y. Okay, let's give in a relations here. Here's some points. Is as a function. Well, let's see. 1 maps to 2, 4 maps to -2, and 3 also maps to 2. Yes, that's okay. We can have 2 x values for the same y. That's fine. We just can't have it the other way. So 95 can be an A, 96 can be an A, no big deal. Okay, what about the inverse? This is the notation for inverse, r to the -1. Okay, this is the notation for inverse, r to the -1. This does not mean 1 over r. Okay, that does mean that for, x to the -1 would be 1 over x. 3 to the -1 is 1 over 3. But that's a variable and a coefficient here, or a number. When you're talking about a function, you don't like put functions under themselves. It's a function. It's more of an idea. So that notation it means inverse. Okay. Write the ordered pairs for the inverse. So 2, 1, -2, 4, and 2, 3. Okay. So 2 goes to 1, -2 goes to 4, and now 2 is branching out and going to 3. So this is not going to work. I can't have a 2 be an A and a 2 be a C or whatever. So this is not a function, and that's okay. You can have functions that are functions, but their inverses are not, and vice versa. Okay, so let's sketch this next little problem. Let's look at our graphs. We're going to interchange the key values here to get the inverse, because that's how you find an inverse. You interchange the x and the y's. So this is what? This point right here is -1, 1/2. And then we're at 0, 1, and then we're at 1, 2, and then we're at 2, 4. Okay, and so to get the inverse, we're just going to interchange those. Okay, so just interchange x and y, flip them, flip-flop. So the domain of f, the domain of f is -1, smear come from. -1, 0, 1, and 2. Okay, so you can see the x values, -1, 0, 1, and 2. And then the range right here, just on this original, is 1/2, 1, 2, and 4. Okay, so let's graph f inverse. So there's f of x. And now f inverse is going to be 1/2, I'll be at -1. 1, I'm at 0, 2, I'm at 1, 1, 2, 3, 4, I'm at 2. So it looks like this. This is f inverse of x. All right? And so now this domain is going to be 1/2, 1, 2, and 4. And then the range is going to be, -1, 0, 1, 2. Okay? So just the x values, 1/2, 1, 2, 4. The y values, -1, 0, 1, and 2. All right, we're going to draw on this line, y equal to x, which is the identity line. Well, if you have y equal to x, you have this identity line, 0, 0, 1, 1, 2, 2, 3, 3, y and x are the same thing. And what do you notice? That you notice that it splits the two graphs in half. It, kind of splits this whole picture in half. And we call that symmetry. The function and their inverses are symmetrical over the interchange of x and y. So you always see a mirror image. This is like a mirror. And the function looks into the mirror and sees its inverse. The same exact thing on either side. That's a line of symmetry. Talk a lot about that in geometry. All right. So sketch the inverse. Here is the inverse of function. So we're going to look here and just flip-flop these points. So 0, 0 will flip-flop to here. 1, 1 will flip-flop, be the same thing, but this will be negative 1, 1. Okay, so this will be 1, negative 1. Okay, this will be 2, 1, 2, 3, 4. So 1, 2, 3, 4, 1, 2. This point is negative 2, 4. So I'm going to do 1, 2, 3, 4, negative 2. So just flip-flopping those like that. And if you draw the line of symmetry, you can see it goes straight, mirror image, okay? And so is the inverse a function. And so if you were to kind of look at those points over there, so we had the point, let's just start with the original. Okay, we had the point negative 4, or sorry, we had the point negative 2, 4. Let's start on the original. Negative 2, 4. We had the point negative 1, 1. We had the point 0, 0. And then we also had 1 go to 1. And we also had 2 go to 4. Okay? So that's great. The inverse then was 4. Let's see. My x and y here. 4 on the inverse. 4 was at 2. 1 was at 1. 0, 0. And then 1 was also at negative 1. Okay, 1 went to 1 and negative 1. And then this 4, this negative, or this 4 not only went to 2, it also went to negative 2. So let's see, let's put a negative 2 here. So 4 branched to 2 and to negative 2. Okay, so 4 is, is paired with 2 and negative 2. 1 is paired with 1 and negative 1. That's not okay. I can't have a 95 be an A and a 95 be a B. So that's what you can't happen. So sketch the inverse. Is the inverse a function? No. No. The original is a function. This inverse is no. For those problems. For that problem. All right. So there's a quick test that can check to see if a relation is a function. It's called the vertical line test. So notice if right here, if I draw this vertical line, just this kind of dashed vertical line, I touch the graph in 2 points there. I touch the graph in 2 points, and that's not allowed, okay? You can't have two y values for the same x. You can't have two y values for the same x. So this right here fails the VLT, because I could draw a vertical line that goes through the graph. So that means that, this was not a function. It failed the vertical line test, and you can see the divergence right there. Whereas the original function, this black parabola here, every vertical line that I draw only touches the graph once. So the function there, the original function there is, of course, a function. The original relation, I should say, is indeed a function. So the first thing we're going to do is use a vertical line test to determine if the relation is a function. Now to see if the inverse is going to be a function. So let's say I didn't draw this inverse. Let's say I didn't graph this inverse. Let's say I'm just looking at this parabola. All right? And that's a function. Passes VLT, so therefore function. Okay, so now I'm not going to graph. I'm not going to graph the inverse. I'm just going to look at this and say, okay, well, if I flip-flop x and y, all right, if I flip-flop x and y, then think about the flip-flop of a vertical, right? Think about a flip-flop of a vertical. That would be a horizontal. So if I draw a horizontal line here and touch into, this is on the original. If I draw a horizontal line and touch the original in two places, that means when I flip-flop X and Y, that horizontal line will flip-flop to a vertical line, right, and fail the VLT on the inverse. So just looking at the original, it needs to pass the vertical line test to be a function, and it needs to pass the horizontal line test for its inverse to be a function. If it passes the horizontal line test, then its inverse will pass the vertical line test. So you use the VLT to determine if the relation is a function, and the HLT to determine if the inverse is going to be a function. Okay? So there's the vertical line test. So the original fails. So it is not a function. Okay, you failed the vertical line test. Okay? And here, vertical line test. Okay, this one passes. So yes, this is a function. Yes, this is a function. I can't draw a vertical line that hits the graph in more than one spot. Okay? So now, what about the inverse of this thing? Will it be a function? Well, let's see. I'm going to test horizontal lines because when everything flip-flops, those would be the vertical lines. Okay? And that passes. So yes, the inverse of this is a function. Okay? Here, I touch a horizontal line. A horizontal line would cross the graph in two spots, which means when it flip-flops, that would be fail the vertical line test on the inverse. And in this one, you can't touch it twice, so this is yes, yes. So both the function and the inverse, both the original and the inverse would be functions. Okay, the equation for the inverse algebraically here, again, this is not 1 over f. This is not 1 over f. It means inverse. This means inverse. All right, so how do you find a function's inverse? The first thing you do is write this as y. You replace f of x with y. Okay? And then you switch. And there you go. You have your inverse. You switch x to y and y to x. You interchange them. So that's basically your inverse, but we want to write it with f inverse of x. Oh, we want to replace y, sorry, with f inverse, so we need to solve for y. Replace y with f inverse. Okay, we want to do that. And so we want to solve this for x. Add 4, and then divide everything by 2. And there's your inverse. And so instead of saying x over 2, I did 1/2 x because I want it to look like a line. So f inverse then is 1/2 x plus 2. Okay? So this third step is solve for y. All right. So y equals negative 1/5 x plus 2. Interchange. Okay. Solve for y. So minus 2. And let's multiply everything by negative 5. Both sides by negative 5. Okay. So both sides by negative 5. So negative 5x plus 10 equals y. So f inverse here is negative 5x plus 10. Okay, so super cool. The property of inverses says that they will negate one another. All right, what do we already know about what's going on up here? We know that these are inverses. Okay, so 2x minus 4 and 1/2 x plus 2. We know those are inverses. We just found it in that first example. Inverses. We know they are inverses. All right, so what happens if I compose them? Let's plug g into f at x. So 2 times 1/2 x plus 2 minus 4. So f is 2x minus 4. So this is 2g minus 4. So this will be x plus 4 minus 4. Look at there. You get They undo each other and arrive at x. They undo each other and arrive at x. All right? And let's do this. Let's plug f into g. F into g. So I'm going to start with g, 1/2, and 2x minus 4 equals, and then plus 2. So 1/2 of 2x is x. I'm just distributing. I distributed here. I'm just distributing here. Minus 2 plus 2, x. They are inverses. So that's the property of inverses. It says if you compose, you get either way, you get x, and you can conclude they are inverses. So quickly, I'm going to do one more. We're going to determine if these are inverses. So these two functions that they gave me right here, are they inverses? So you have to test both ways. You have to test the first test, we have to plug g into f at x. So 5x plus 3 minus 3 over 5. Cancel, cancel. X. Okay? So we got x. So far so good, but you have to show it happens both times. Sometimes it'll only happen one way and not the other, and so you have to do the test twice. So I'm going to plug f of x into g. So 5 times x minus 3 over 5 plus 3. So I'm just plugging this equation into this equation at the x. X minus 3 plus 3, and that is x. Okay? So since the composition of f of g is x, and since the composition of g of f is x, g of f of x is x, they are indeed inverses of one another. All right. That's the end of our video. Thanks, guys. And, hey, that's the end of Chapter 6. So, hope you found that helpful.